Good evening, everybody. Today we will complete the presentation of chapter 3, and next week on Tuesday we can have a quick review in case it is needed before we have exam 1 on Thursday that will cover chapter 1, chapter 2, and chapter 3. The first topic of today's class is equation of state, or EOS. So it is reasonable to think that variation of pressure temperature on the compressibility factor for gas expressed as an equation. So these two equations show an example where a compressibility factor Z here is formulated in terms of a series of terms here, function of temperature and pressure. So in here it's showing a unlimited series of term. Once again, it is a function of temperature and pressure, and then we have a series of constant, so B, C, D, and so on. And then in the second equation we represent it in different form, but you can see each term has a similarity here. So in here on the second equation, Z equal to 1 plus B here is a function of temperature divided by V. So in here we replace pressure or we substitute pressure properties by specific volume. So these two equations is an example of representing Z as a function of pressure and temperature, or temperature and specific volume. So this two equation is usually called a virial equation of state, and the constant B, C, D, and so on are called virial coefficient. So this kind of PVT relationship of gases is known as equation of state once again. So equation of state is an equation representing relationship between P, V, and T. Next topic will be evaluating properties using ideal gas model. So let's go back again to this compressibility chart on the right top figure. So in this case, once again, on the horizontal axis we have a reduced pressure, so PR. So just to remind you, PR here equal to P over PC. So P is the corresponding pressure and PC is the critical pressure. So see the condition here where pressure is small, so P is small, so it's mean PR is also small, so it is somewhere on here. So as you can see in here, when we have a PR close to 0 or approaching 0, so you can see on this generalized compressibility chart that the compressibility factor Z is approximately 1. So last time I showed you an animation about the blue dot, that it goes to the same point of Z when we reduce PR to 0. So once again, if PR get smaller and smaller, then Z equal to 1. So at such states, we can assume with a reasonable accuracy that Z equal to 1. So at such state, it means when a PR approaches 0 here. So, and from the condition where Z equal to 1, here it is called ideal gas equation of state. So once again, if we have a condition PR close to 0, then we have a condition that is called ideal condition, and from this ideal condition we can apply ideal gas equation of state. So ideal gas equation of state here is the condition where z equal to 1. So with z equal to 1, we have equation 3.32, because the original equation for equation 3.32 is actually P times V equal to ZRT. So Z equal to 1, so you can drop out a Z, then you only have equation PV equal to R times T. So this is a very important for ideal gas equation of state, Z equal to 1. Then we have equation 3.32 where PV equal to R times T. So these two schematics showing the comparison between ideal gas and real gas. For ideal gas, once again, we have Z equal to 1. For real gas, Z can be 1, can be below or above 1. So in real application, there is not ideal gas, but once again, at some condition, we can assume certain gas behaves like an ideal gas. Okay, so we have ideal gas, we have real gas. For ideal gas, Z equal to 1. For real gas, Z can be 1, below 1, or above 1. So go back again to equation 3.32. I write it down again here that we have a P times specific volume equal to R times T. So R here is the gas constant, it's not universal. The one that's called universal is when we have R with over bar. Okay, so here is gas constant, so R. So PV equal to RT is for ideal gas, where Z equal to 1. So there are three alternative forms of equation 3.32. So the first form here is when we substitute specific volume small v here by this equation, that the specific volume equal to volume divided by mass. Okay, remember that specific volume equal to 1 over rho density, and I believe the formula of density is more popular. So, and then density is, you know, it is mass divided by volume, right? So in here I have volume divided by mass with this equation. Okay, so if I substitute specific volume by V, so capital V divided by mass in this equation 3.32, then I will get equation 3.33. P times V, capital V here, equal to mRT. So I believe you use this equation when you learn ideal gas constant in the physics class. So P times V, volume, equal to m. M here is mass of the substance, times R, gas constant, times T, temperature. The second form is when we substitute V by V on a molar basis, so with over bar here, and as well as replacing R by R over bar. So in here R equal to R over bar, this one is per molar basis, divided by the molecular weight, the capital M. So if we substitute both V and R by this equation, then we will get equation 3.34. P times V with the over bar here equal to R with the over bar times T. So R with the over bar here is the universal gas constant. Universal gas constant. So this is the one with the number of 8.314 kilojoule per kilomole Kelvin. Okay, so universal, so it's mean it is the same for any gas. The third term here is when we use this formula that the specific volume in molar basis, it's equal to the volume divided by N, and here is the number of mole. So if we apply this correlation to equation 3.32, then we will get equation 3.35. P times V, here is capital, so this is volume, equal to N, the number of mole, times R, R with upper bar, so universal gas constant, times T. So you can see in here, we have four different formula or four different form of ideal gas equation of state: equation 3.32, equation 3.33, and up to equation 3.35. So you can use any of these four equations according to which data is given in a problem. So if we look at further the condition under ideal gas condition, so by investigating equation 3.32 up to 3.5, it will indicate that the specific internal energy depends primarily on the temperature. So with this fact, we can assume a reasonable accuracy. So mention reasonable accuracy. Mention ideal gas is an approach or an idealization. So, but we still have a reasonable accuracy when we assume a gas under ideal state when the PR once again goes to or close to zero. So back to this statement. So U or specific volume here depend primarily on the temperature. So in this case, we can formulate it as equation 3.36, that U is only a function of temperature. So in reality, U is a function of two parameters, either pressure and temperature, or temperature and specific volume, and so on. So for the gas behaving ideal condition, so U is only a function of temperature, equation 3.36. So with equation 3.32, let me write it down again, 3.32, so P times specific volume equal to R times T. So this is equation 3.32. So with equations 3.32 and 3.36, the enthalpy also depend on temperature alone. So with this, then we have equation 3.37. So if you remember, enthalpy doesn't have any physical meaning. It just help us to shorten this U plus PV. Okay, U plus PV equal to H, or enthalpy. So U is only a function of temperature, and PV, because it is ideal gas, so you see here equation 3.32, you can replace PV by RT. So you can see here in equation 3.37 that H is also a function of temperature alone. Okay, because R here is not a function of temperature. Okay, so in ideal gas condition, U is only a function of temperature alone. H is also a function of temperature alone. So collecting results, so a gas model as an ideal gas adheres to equation 3.32 up to 3.35. So it is four different appearance of equation of state. Once again, 3.32 up to 3.35. And equation 3.36 for the formula of internal energy, and 3.37 for the formula of the enthalpy. Okay, so we have four equations different appearance for equation of state, plus 2 equation representing the formula of U as a function of temperature only, and enthalpy, equation 3.37 as a function of temperature only as well. So next one. So while the ideal gas model doesn't provide an acceptable approximation generally, so in the limiting case, and I mentioned to you, limiting case here means that when the PR is close to 0, so it is justified for use, and indeed commonly applied in engineering thermodynamic at such state. So once again, this case, if I have a gas and PR here is close or approaches 0, and at the same time you might have TR going high, then we can assume a certain gas behave under ideal condition. So if you want to check whether this approximation is good or not, go back again to the compressibility chart. So for example, if you have a certain gas, temperature is given, pressure is given, then you will be able to get what is TR and what is PR. So once you have these two parameters, PR and TR, you can go to compressibility chart and check what is Z. Okay, if PR get lower and the same time TR get higher, or even you only have PR gets lower, approach to 0, then your Z will close to 1. So it's mean the approximation of ideal gas condition for the corresponding gas is acceptable. Otherwise, then we need to rethink about different gas equation of state, which will be studied in detail in thermodynamic too. And if try to be familiar with the compressibility chart, so this is figure A1 through A3. So once again, figure A1 up to A3, the compressibility chart as a function of TR and PR. Let's have a look on this example. So the question here is, we need to analyze air as an ideal gas undergoing a thermodynamic cycle. So thermodynamic cycle. So we use this cycle now on this example. If you remember, thermodynamic cycle or any cycle is when the process go back again to the starting point. So it's mean delta U for a cycle equal to 0. So in this example, we have 1 pound of air in a piston cylinder assembly. So 1 pound of air in a piston cylinder assembly undergoes a thermodynamic cycle consisting of 3 processes. For the process number 1, so it's changing the state from state number 1 to state number 2. So it occurs under a constant specific volume. So in here, delta of V equal to 0. So isochoric, so constant volume process. And then second process, it's changed from state number 2 to state number 3. It's occur under constant temperature expansion. So in here, delta T equal to 0. And what's happened with the delta V? So it increases because it's expansion, right? So in here, delta V or volume is a positive, so expansion. And then the third process, so it's change state number 3 back to state number 1 with a cycle, so back again to state number 1. It occurs at constant pressure and compression. So in this case, we have delta P equal to 0 and delta V is less than 0. So the condition at state 1 is given here. We have 500-degree Rankine. So okay, here is a British unit, and pressure is 1 atmosphere. So state 1 is given here, 540-degree Rankine and 1 atmosphere. At state 2, the pressure is 2 atmosphere. Okay, state 2, pressure is given here, 2 atmosphere. And then employing ideal gas equation of state, the first question is sketch the cycle on PV coordinates. Second question is determine the temperature at state 2 in degree Rankine. So the question here is what is T2. And question number 3 here is determine the specific volume at state number 3, specific volume, so small v here, V3, in cubic feet per pound. Okay, let's try to solve this problem. As you might know already, so you need to complete this step. So what is known there? So air executes a thermodynamic cycle consisting of 3 processes. So from state 1 to state 2, and then state 2 to state 3, and then back again from state 3 to state 1. And then the characteristic of each process is given. For example, process 1 that change state 1 to state 2, V constant, so delta V constant. And then process number 2, temperature is constant, and process number 3, pressure is constant. And then P1, T1 as well as P2 is given here. And then there are 3 questions there. What we need to find out here is the sketch, and then T2 and V3 here. The next step you need to write it down is the engineering model or assumption. So the first assumption here, the air is a closed system, so it means there is no transfer of mass, so there is no mass in and mass out across the boundary. It's closed system. And then the second engineering model or assumption here is that the air behaves as ideal gas. And assumption number 3 here, that piston is the only work mode here. So there might be other work on this problem, but here we assume that the work done by, or the work applied to the piston is the only work mode. So next one is looking at the sketch of these 3 processes on PV diagram or PV chart. So in here we have we put state number 1 arbitrary here. So we have state number 1 here, and we also show you the constant line pressure, so the orange line. So this is the constant line pressure at 1 atmosphere. So state number 1, oh sorry, not constant pressure line, this is constant temperature line, so at 540-degree Rankine. So where is the dome? Because we don't see the dome here on this PV diagram. Usually we see the dome, right? So we don't have the dome here because the dome is way maybe beyond this PV diagram. So the dome is somewhere here, because this one, these 3 states are gas state, and for sure this is superheated condition. So we don't draw the dome here just for the ease of this chart representation. But if you wanted to make the dome, so the dome should be somewhere here. So like somewhere here. Okay, go back again to this PV diagram. We have state number 1. So P is given there, T is given, so 1 atmosphere and 540-degree Rankine. And then let's go to state number 2. State number 2 here occurs under constant volume, so that you have a straight vertical line connecting state number 2 to go to state number 1 to state number 2 here. So why is going up? Because P2 is 2 bar. it is given in the problem, so it's going up. So in here we have a constant volume process that increases the pressure from 1 atmosphere to 2 atmosphere. And then process number 2, exchange state 2 to state 3, it's happened under constant temperature. So that we have a second orange line here. So this one is constant line temperature at 1080. So we will have a look this temperature because we need to calculate it. But in this chart, it's shown you before or prior to the calculation. But later on, we'll calculate this one. So once again, so from state 2 to state 3, so it's occur under constant temperature. So T equal to C or delta T equal to 0. And then the last process is change state 3 back to state number 1. It occurs under constant pressure. So in here you have a straight horizontal line. It's constant pressure. That's connecting state 3 to state 1 there. Okay, please review again this one when you're at home. Make sure that you understand on how to draw this process line in the PV diagram. Okay, go back again. For the question A, we have made it, and then B, in here the question is temperature at state 2. So in this case, we can apply ideal gas equation of state. So PV equal to RT, and then if you apply this to state number 2, so you can put a subscript 2 on each of the parameter there except for R, because R here is the same for all states in this problem. It's just one gas type. So in here we have T2 equal to P2 times V2 divided by R. This one. P2 is given there, 2 atmosphere. What we need to find out is what is V2, specific volume at state 2. And if you remember the process from state 1 to state 2, let me redraw the PV diagram again. From state 1 to state 2, it occurs under constant volume. So it's mean that V2 equal to V1. Okay. So this case, we calculate V1 first because P1 is given, T1 is also given. So this one is the formula of V1. And then V1 equal to V2. So this is if we substitute a V2 by this formula, then I have this one. The T2 equal to P2 divided by P1 times T1. So in this case, you don't need to make a conversion of unit because it's just showing the ratio of pressure. So the atmosphere unit cancel out, and then the equation is the temperature in a degree Rankine. So T1 is also in degree Rankine, so you don't need to change the unit. So T2 is a double of T1 here, so it is 1080 degree Rankine. Go next to question C. So it is the specific volume at state number 3. So let me continue the drawing here, PV diagram. So this is the constant temperature line. So I think I have this one. So this is state 3. So question 3 is what is specific volume at state 3, or question C, sorry. So in this case, we have once again apply PV equal to RT, and then specific volume at state 3, we have V3 equal to R times T3 divided by P3. So what is known in state number 3 here is that it has the same temperature as state number 2 because the process connecting state number 2 and state number 3 occurs under constant temperature. So T3 equal to T2. And then another given condition here that state number 1 and state number 3, they have the same pressure, because once again the process connecting state 3 back to state 1 occurs under constant pressure. So in this case we have P3 equal to P1. So you have T3, you have P3. You can plug in all this number and use the ideal gas equation of state. You will get V3 here. Okay, so in here we have R over bar 1545. The unit is feet pound force per pound mole degree Rankine, and then this M 28.97 is the molecular weight of air in British unit. And then you have temperature 1080 degree Rankine, and then pressure is 14.7 psi. In this case, you see here there is imbalance of the length unit. So in this case, for the R, I have the unit in feet, and then for the pressure I have unit in inch. So in this case we need to apply a conversion factor here between square feet and square inch, as you might know that 1 feet equal to 12 inch. So because this is in square, so you need to multiply it again by 12. So 1 square feet equal to 12 times 12 square inch, or it's equal to 144. So if you plug in all number, you have V3 equal to 27.2 cubic feet per pound. And if you wanted to know where you get M, the molecular weight of air, so go to table A1E. Why E? Because it is in British unit. For a gas obeying the ideal gas model, specific internal energy depends only on temperature. So hence, the specific heat under constant volume condition defined by equation 3.8, you can look back on the previous slide, is also a function of temperature alone. So hence we have equation 3.38 here. So Cv is only a function of temperature, and this is because U is a function of temperature only. If we modified this equation 3.38 and make integration of the du, because in here from equation 3.38 I have du equal to Cv dt, and if I make an integration, then I will get equation 3.40. So U at temperature 2 minus U at temperature 1 equal to the integral from T1 till T2 Cv dt. Once again, this is for ideal gas. Similarly, for a gas obeying the ideal gas, specific enthalpy so depends only on temperature. So if you look at back again on the previous slide to see equation 3.9 that define Cp, so Cp equal to dH over dt. So in here we will have equation 3.41 where Cp only a function of temperature, so dH over dt. Why? Because H here for ideal gas, it is only a function of temperature. So similarly, if we make an integration, so we'll have equation 3.43. This chart is showing Cp for different gases, so CO2, H2O, as a function of temperature. So this is in degree Rankine, but you see here there is second horizontal axis showing the temperature in SI unit, so in Kelvin. So generally, Cp of the gas increases with the temperatures. In there, most line has a positive slope. That's mean the Cp, so in here it is represented as Cp over a universal gas constant, increases with temperature. So now go to table A20. So table A20. So in table A20, you will see a Cp for several ideal gases there. So we have here, I make a screenshot here. So we have a Cp for air, and then nitrogen, oxygen. So, and this is a function of temperature. So we have a Cp, we have Cv, and then we have K. So if you remember, K is the specific heat ratio. So it is Cp over Cv. And then the first column, you have the temperature. And then on the bottom side in here, you also have CO2, and then CO, carbon monoxide, and hydrogen. So once again, if you need to get Cp as a function of temperature for different ideal gases, then go to table A20. Okay, now go to table A21. In table 21, it shows Cp also for different gases, but look at the top of table A21, they formulate Cp here as a polynomial function of temperature. So in here you see Cp over universal gas constant equal to alpha plus beta times T plus gamma times square T for delta times cubic T, and so on. And alpha, beta, gamma, delta, and so on here is shown in table A21. So in the first row here, we have constant for CO, and then CO2, and so on. The data representation for Cp in terms of the polynomial function here is very useful when you want to include or you want to calculate Cp and use it in programming. So you can still use a table, but usually it takes a time because you need to build a code to do a lookup table, track the temperature, where is the location of the grid point, and so on. But with this polynomial formula, you can apply right away in your code, and then the code will calculate a Cp as a function of the temperature. So right now there are two different representations of Cp. So one's using a lookup table, so table A20, and then a second one is using table A21. So in this case, Cp is formulated as a function of temperature in a polynomial formula. So this is just to recap about the ideal gas model relationship. So on the first part here, we have several form of the ideal gas formula. We have PV equal to RT, equation 3.32, and then we for the ideal gas, U is only a function of temperature. So ideal gas, so U is only a function of temperature, as well as H. H also a function of temperature. If you remember, H equal to P plus H equal to U plus PV. So U is a function of temperature, and then this PV you can replace it by RT. So thus H also a function of temperature only. And then on the second part here, it's shown the formula for the change of the specific internal energy. And then if we have a constant Cv, then this Cv can be put outside of the integral form so that you have equation 3.50. So delta U equal to Cv times delta T. Okay, and then at the next part we have the formula for the change in specific enthalpy. So it is integral Cp dt, and like in the case of U, if Cp is constant, then it can put outside of the integral form and you will get equation 3.51. So for constant Cp, then delta H, so difference in enthalpy, equal to Cp times the difference in temperature. So this formula will be put in the equation sheet. You don't need to memorize it, but you need to be familiar. You need to understand when and where you need to use this formula. So we have a K, we have also, look at here, this is another form of the Cp. When K is given, then you can calculate it. So K is given, and then R is coming from universal gas constant over molecular weight. And similarly, you also have the formula of Cv here, so a function of R and K. So once again, you don't need to memorize, but you need to understand how, when, and where you need to use each of these formula. So this is just a repetition from the previous slide. So when the specific heats are modeled as a constant, then you can use equations 3.50 and equations 3.51. So delta U equal to Cv times delta T, as well as delta H equal to Cp times delta T. So for several common gases, evaluation of change in specific internal energy and specific enthalpy can be seen in table A22 and A23. Okay, so and then table A22 applies to air, and once again it is modeled as an ideal gas. So this is the screenshot of table A22. So this is for air, model as an ideal gas. So on the first column, you have a temperature. See in here, you only have temperature column here. Why? Because the properties of ideal gas, in this case air, is only a function of temperature. So in here, the first column, I have temperature, and then second one, I have enthalpy, and then next one, I have specific internal energy. Next one I have entropy. So hold on this one. So in chapter 5 and 6 I will introduce you about this entropy, and then similarly in the next one you also have enthalpy, U as a function of temperature at higher level. And you can also see here a PR and VR at different temperature as well. This one is the continuation of table A22, so at higher temperature. So starting from 750 Kelvin through here we have up to 2250 Kelvin. So as I mentioned to you previously, you have a SI unite type table. So in here table A22. And then you also have a British unite type table with the addition of E in the name. So you have table A22, and then if you go to table A22E, so you have a similar table, but it is under British unit. So the temperature will be in degree Rankine, enthalpy will be in BTU, and so on. Let's have a look on this simple example. So evaluate the change in specific enthalpy in kilojoule per kilogram of air, model as an ideal gas, from a state at T equal to 400 Kelvin to a state where T equal to 900 Kelvin, using expression in table A21. So expression in table A21. If you remember, in table A21, Cp is formulated in polynomial form as a function of temperature. So if you remember, table A21 contains like the constant for alpha, beta, gamma, and so on. And then compare the result with the value obtained from air table. So table A22. Okay, so we'll compare the Cp result between table A21 and table A22. So this is the Cp formula from table A21. Once again, it is in terms of polynomial form as a function of temperature. So we need to find out what is alpha, beta, gamma for air. So it is this one. So you need to replace alpha, beta, gamma, and so on with the number for air from table A21. So back again to the problem, and now we solve it. So H or delta H equal to the integral Cp times dt. Okay, so in here it is from T1 through T2, and then you substitute Cp here with the polynomial function, with this one. Once you substitute Cp with this polynomial function of temperature, then you make an integration. So nothing complicated here. So you just apply a formula for the integration. So the integral of alpha dt will be alpha t. So in here, or alpha delta t. And then beta t here will result in beta over 2 times t square. And then here, because the integral is from t1 through t2, you have beta over 2 times t2 square minus t1 square, and so on. Okay, and then the alpha, beta, gamma, and so on, you get it from table A21, and then you plug in all number and you will get delta H, so different in enthalpy, and you get here is 531.96 kilojoule per kilogram. Okay, the next option is by using table A22. So table A22. So now go to table A22 and then find out what is the enthalpy of air, model as ideal gas. First one is at T1 equal to 400 Kelvin. So go to table A22. So at T1 equal to 400 Kelvin, I think you will get enthalpy equal to 400.98 kilojoule per kilogram. And then T2, it is 900 Kelvin. Go same table. You might need to go to the next page if the temperature 900 is not at the same page as the one for 400 Kelvin. Then you will get H2 equal to 932.93 kilojoule per kilogram. So then once you have H1 and H2, you can calculate delta H equal to H2 minus H1. You can use your calculator, plug in this number, and you will get 531.95 kilojoule per kilogram. I think it's pretty close. So you can check previous slide. It is 531, the same, but the two number after the point here is not the same. So it's pretty close. So either use table A21 or A22, it doesn't matter. You just pick up which one that make you more convenient, or maybe it take less time to get it. Okay, we have completed the presentation for looking at the properties of a substance under ideal gas. And the last class we also look at the gas substance properties under different phases, so liquid, and then mixture within the dome, and then superheated state on the right side of the dome. So this slide is just a recap about the evaluation of properties for substance. So first one is you need to use thermodynamics properties table if full tables are available. If you look at the end of the book, you will get a full table for water, ammonia. So ammoniac, it will be very useful table when we deal with refrigeration and so on in chapter 10, as well as refrigerant R22 and refrigerant R134A. So the book has a table for propane as well. So propane as natural gas is a popular fuel right now because it is cheaper. So the next one is you need to use two independent properties to fix the state. Okay, so point number one here. So when the state is on the left side of the dome or on the right side of the dome, once again, you need to have two independent properties, either pressure and temperature, or pressure and specific volume, or specific volume and temperature, and so on. So next one, this is very important, the one in blue color here. In the two-phase region, P and T are directly related. So P and T are not independent in the two-phase region within the dome, inside the dome. And they cannot fix the state. So if you want to fix the state within the dome, you need to have either pressure and specific volume, or temperature and specific volume, or pressure and quality, or temperature and quality. Okay, so next one, tables are organized based on pressure and temperature, and you saw it already. Table A2, this is saturated table based on temperature. Table A3, this is saturated table based on the pressure. Table A4, still for the water, this is a superheated table based on the pressure and temperature. And the table A5, this is for water, compressed liquid water, so it's based on pressure and temperature. So number three, so how do we identify the phase or phases? I did mention it to you in the last week classes. So for example, if a T1 is given and then P1 is given, and for sure you don't know whether the state is compressed liquid or within the dome, or it is on the right side of the dome, you can use table A2 to get the corresponding P set, or you can use table A3 for the corresponding T set. Okay, assuming you use table A2, then you get P set. Now you compare between this P set and P1. So if P1 is greater than P set, then this is compressed liquid. Okay, compressed liquid. Then you go to table A5. Conversely, if P1 is less than P set, then you go, or then it is a superheated condition, and you go to table A4. Okay, it should be straightforward and simple how to determine the phase of a substance based on a given pressure and temperature. So number 4, when full tables are not available, then you can use the generalized compressibility charts for evaluating P, V, and T. If you remember the generalized compressibility chart, this showing the dependency of Z, compressibility factor, as a function of PR and TR. So PR equal to P over PC and TR equal to T over TC. So once you have Z, then you can calculate other properties based on a given properties. Number 5, we just look at this. If a gas behaves as an ideal gas, so in here PR is close to 0 for any temperature, then you can use ideal gas equation to find P, V, or T based on a given properties there. And then you can determine U and H from appropriate ideal gas tables, for example table A22, or you can use table A21 to calculate Cp first, and then you calculate enthalpy. And then in scene here, you can determine the change in U and H from the appropriate equation. So we also have shown you how to calculate a change in U and H in case Cp and Cv are constant. Last topic for this chapter 3 is polytropic process. So I already introduced you this polytropic process in previous chapter. So a polytropic process is a quasi-equilibrium process described by equation 3.52. So P times V to the power of n equal to constants. So also the exponent n here may take on any value from minus infinity to positive infinity depending on the particular process or depending on the characteristic of the process. So for any gas or liquid, when n equal to 0, so it's mean P times V to the power of 0 equal to constant, so it's mean P equal to constant, then the process occurs under constant pressure, or it's called isobaric process. And then for any gas or liquid, when n equal to plus minus infinity, so it's mean here we will have a constant volume process or isometric process. For ideal gas, when n equal to 1, so we have P times V equal to constant. The process actually is a constant temperature process. Once again, for ideal gas, when n equal to 1, the process is a constant temperature process or isothermal process. So this is some of the formula for polytropic process. So between two states you have this one. I think you saw it already in chapter 2. So from state 1 to state 2, if it is a polytropic process, we have this formula. So P1 times V1 to the power of n equal to P2 times V2 to the power of n. And then you can make some adjustment here to get equation 3.53. So the ratio of pressure here equal to the ratio of volume to the power of n. And then you can also apply this formula to get equations 3.54 and equations 3.55. This is just a review. So equations 3.54 is when n is not equal to 1, and for n is equal to 1 you have equation 3.55. So once again, you don't need to memorize this one, but you do need to understand when, where, and how to use this formula. For ideal gas, you have additional equation here, equation 3.56. This shows the relationship of the temperature ratio to the pressure ratio, and we need to put this power, so n minus 1 divided by n. So the temperature ratio can be also formulated as the volume ratio to the power of n minus 1. Once again, equation 3.56 here is for ideal gas. So similarly, you can substitute P. So in here I have P dV. So you can substitute P here by the ideal gas formula, with this R times T divided by V, and then dV. So if you do a integration of this equation, then you will get equation 3.57, and equation 3.58 depending on the value of n. So for n equal to 1, you have 3.58, and then for the ones that doesn't equal to 1, you have equation 3.57. Once again, you don't need to memorize this formula. I will give all the formula in the equation sheet from the exam. You just need to be familiar. You need to know when, how, and where to use this formula. Now let's have a look on this example. So air undergoes a polytropic compression. So the volume decreases in a piston cylinder assembly from pressure equal to 1 atmosphere, temperature of 70 degrees Fahrenheit, to the final pressure of 5 atmosphere, employing the ideal gas model with constant specific heat ratio, so constant K. Determine the work and heat transfer per unit mass in BTU per pound, so it is in British unit, if for A, n equal to 1.5, B, n equal to K, and then another clue here is evaluate K at T1. Okay, K need to be evaluated at T1. So for sure we need to start with this step. What is known there? So air undergoes a polytropic compression process from a given initial state to a specified final pressure, and then the equation is work and heat transfer each in BTU per pound. And then next step is to make a schematic. So we have a PV diagram here. So it is a compression process. So volume decreases, pressure increases, so it's changing from state number 1 to state number 2, going to the left, because the volume, once again, the volume decreases, and then going to the left and up, because pressure increases. And then this is the schematic of the system. So it is within a piston cylinder assembly, and the system here is only air with a given P1, T1, and P2. And this is the engineering model or assumption. So it is a closed system, and then the air behaves as an ideal gas with a constant specific heat ratio evaluated at T1. And then the compression is polytropic, and piston is the only work mode there. And number 4 here is there is no change in kinetic energy and potential energy. So delta KE equal to delta PE equal to 0. Okay, so for the work, for sure we have this formula. So integral from state 1 to state 2, P dV, and then we can use equation 3.57. We have W over M equal to R times delta T over N minus 1. And then the heat transfer can be calculated from the conservation equation. So first law of thermodynamics. So Q equal to W plus delta U. And then we can also have a look on equation 3.47b, that when specific ratio is constant, Cv is also constant. So it's in here, equation 3.47b, I put it on the top right corner here. So once again, if I have constant K, I will have also constant Cv, because Cv is only a function of R and K. So R is constant, and then K is constant, then Cv is constant. So in here, I can substitute U here with Cv times T. So next one, I have this formula. So now I'm ready to go back to each question here. For A, n equal to 1.3. So first you need to get the temperature at state 2, and then you can apply ideal gas formula here. So for the ideal gas formula, the ratio of temperature can be formulated as the ratio of pressure to the power of n minus 1 over n. So you just plug in all number here. We have T1 530, and then P2 is given there 5 atmosphere, P1 is also given there 1 atmosphere. The equation for T2, or we need to find out T2 in degree Rankine, that can be converted to degree Fahrenheit later on. So in here we don't need to convert the pressure unit because it's showing it just the ratio, so it will cancel out whatever the unit of the pressure there. So if you plug in all number here, T1, P1, P2 and so on, n equal to 1.3, you will get T2 768 degree Rankine, or it is equal to 308 degree Fahrenheit. So you got T2, then you can plug in T1, T2, n and so on to get the work. See here, the work is negative. It means the work is done on the system. So this is a compression process. It makes sense because we need to apply a work from outside, from the surrounding, to the system to do a compression process there. So we already get work there, and then we need to get CV to get U. So, and K is evaluated at T1. So in here T1 is 70 degree Fahrenheit, or this coming from the conversion of this 530 degree Rankine. So we have T1 at 70 degree Fahrenheit, and then go to table A20E to get what is K there. Okay. Table A20E at 70 degree Fahrenheit, you will get K equal to 1.401 and CV equal to 0.171. Okay. Alternatively, you can also get CV using equation 3.47b. I show you in the previous slide on the top right part there. So CV equal to R divided by K minus 1. So K you get it from table A20. R is R for the air, and you will get CV as well. So it's up to you. You can obtain it from the same table, or if you want to calculate it, no problem as well. So you see there, both are the same. Okay, so once we got CV, then we can plug in all number there. So because we already have W over M here, then we will get Q here. So Q equal to minus 13.96. So it's minus. So it's mean there is a heat transfer or energy transfer in terms of heat from the system going out to the surrounding. Okay, we have completed part A, and then go to B. B here, N equal to K. So specific heat ratio. And then if we substitute equation A and C, so we can see equation C here, equation A is in the previous slide, then you will get this one. See there, it's showing interesting. So for N equal to K, so Q equal to 0. What does this mean? So it means that for a polytropic process where N equal to K, the process occurs under adiabatic condition. So there is no heat transfer. Okay, we have completed chapter 3, and if we still have time, so the TA will show you the solution for homework 3. Once again, next week on Thursday we will have exam 1 that cover chapter 1, 2 and 3, and then on Tuesday, if you have any question, we can review each of the chapter so that you have a good time, you can have a well preparation for the exam number 1.